All right, I think we're at time. Yeah. Good afternoon. So we are going to talk about the next part of chapter 18 today. We did a bunch of reactions. The majority of them were adding something onto a benzene ring. So we looked at six different things we can add to a benzene ring on Wednesday. And then today we're going to essentially move to the next step, which will be, what if we want to add a second substituent to the ring? Before we start that though, I do want to just announce, although I'm sure you guys probably all saw, that the first test is graded. So of course you can see your score, but in addition to that, if you go back and look at your exam, I have written on it. So you'll see notations on there. And then I filled out a rubric for each student. So the same rubric that I had posted, I filled that out for each of your unknowns as I went, and I saved them with your first name. So it will probably be like close to the comment section, but you'll see a PDF with your name, and that is the rubric that I filled out for you. So if you have any questions, you are always more than welcome to ask me. But yeah, that is available and ready for you. Along the same note, so grading. Oh, is my mic bad today? Make sure I don't have it. Just making sure everybody's plugged in.
Professor, I could hear you pretty well.
Okay. Some static, huh? All right, let me just make sure I got all my USB, my 1 million USB cords all plugged in completely here. I think we're good. Okay. So grading, your second lab report is technically due today. And I say it that way because I haven't gotten the first one fully graded yet. I've gotten through about a quarter of all the students, so between both classes. And so because I do want you to see that and use that feedback before you turn in your second one, or at least have that option, I changed the availability on the lab report that's due today until Wednesday. So okay, let's start that sentence over. You have until Wednesday at 11:59 p.m. to turn it in. If you've already turned it in, you can always resubmit it if you get yours back and you get last week's back and you realize you want to make some changes. That's completely okay. So just throwing that out there. I'm going to work on grading them today and then tomorrow as well. So I should be able to get them all done by tomorrow. I will get them all done. How I do it that's me to figure out. So I think that's it for scheduling and housekeeping kind of stuff. Let's get over here to let's get to the right slide. Right here. Any just kind of general questions before we get started with lecture today? Okay, I think I am all set up then. Okay, so as I mentioned, we are going to be talking about adding that second and eventually third and fourth substituent. So today, though, we're going to be focusing on what happens when we add a second substituent. And it doesn't matter what we're adding to the ring. All that matters is what's already present on the ring. So the example that's down here is that there's a methyl group. Now we are going to add an NO2 group with nitric acid and sulfuric acid, but the product that we're making is going to have a methyl group on it. And then the question is, where does that nitro group add? Is it going to add ortho, meta, or para to the original substituent? And it's only based on the substituent that's currently on the ring. So in this example, we're adding a nitro, but it could have been another methyl, a chloro, a sulfone, anything, and the answer will be the same. So we're only looking at the original starting material to answer the question of where does it add. There are two sides that we have to look at to decide what our product will be. The first one is the rate of reaction. And so we're not getting into like kinetics and actual numbers here. We're just looking at it from a comparison of if this is how fast benzene reacts when we add a substituent, is it going to go faster than a plain benzene, or is it going to go slower than a plain benzene? Plain benzene is a weird way to say that. And unsubstituted benzene would definitely be a better way to say that. If it's going faster than benzene, we say that the substituent is activating the ring. So this is faster than just a regular benzene. And if the substituent is making the reaction go slower, then we say that it is a deactivating substituent. And we're going to talk a lot. I mean, this is pretty much all of today, is defining those two terms, talking about what substituents fall into those categories and why they fall into those categories. And then the second side that we're looking at is sterics. So if a substituent is making the reaction go faster or slower, what does that mean? Is it going to add the new substituent, ortho, meta, or para, or maybe a mixture? And so we're going to look at all sides of this with lots of categories, really. Today's definitely a labeling and categorizing kind of day. This is another kind of general introduction slide, but we're going more into the terms here. So we're dividing it into activating and deactivating. And our activating substituents are going to increase reactivity, or another way to say that is it's just going to make the reaction go faster. And our activating substituents are all electron donating groups. And again, we're going to talk about how they donate those electrons and what groups fall into that category over the handful of our next slides. The reason why an electron donating group would make the reaction go faster, though, is because it's going to make benzene a better nucleophile. So I'm going to go back a couple slides to something we talked about last week. When we looked at all of our mechanisms, so we had our 6 substituents that we could add, they all had the same basic mechanism pattern. The first step was that nucleophilic attack, so this arrow right here, and we started from the pi bond of our benzene ring because our benzene ring is our nucleophile. So a nucleophile needs to be electron rich. So if our substituent can add electrons into the ring, it's making it more electron rich. That makes it a better nucleophile. That's going to make this step go faster. So that's one way that these types of substituents can make the reaction go faster. They are making benzene into a better nucleophile. The other way that they can make the reaction go faster is they help stabilize that transition state. So I'm going to go back to that mechanism again. So we have three parts to our mechanism. We had that first nucleophilic attack. We had the resonance of our carbocation transition state in the middle there, and then we ended with the proton transfer. So if we look at the resonance of our carbocation, two things I want to point out. One of them I mentioned a handful of times last week, but I'm going to keep mentioning it today because it's important. Our carbocation, as it moves around that ring, it hits every other position. And if we have an electron donating group that lines up with one of those positions, it can donate its electrons towards that carbocation and help stabilize it. So our electron donating groups can help make our benzene a better nucleophile and help stabilize that transition state. So if we think about our energy diagram, having that electron donating group is going to make that first hill shorter because it's going to make benzene more reactive, and it's going to make the transition state energy smaller because it has added stability to it. So overall, the reaction is going to be faster. All right, so on the other half, completely opposite. Oh, and actually one more thing before we switch over to the other half. The activating substituent is just represented with a letter Z down here, just to say that it's going to react faster than our unsubstituted benzene in the middle. So just so you know what that means down there. Okay, so let's switch over to our deactivating substituents. And these are going to decrease the reactivity. So that means that they are going to go slower than an unsubstituted benzene. So that's represented with a Y down here on the bottom. And these are all electron withdrawing groups. And the reason why they're making the reaction go slower is essentially the opposite reason of why our activating groups are making the reaction go faster. Benzene needs to be a nucleophile in that first step. So if these substituents are withdrawing the electrons from that group, it's going to make benzene worse at being a nucleophile. And this one's a little bit different, but because they can withdraw those electrons from the benzene ring, it actually adds more resonance to the benzene before it even reacts. That's going to make benzene more stable to start with. So when we talk about our energy diagram for the reaction, if we're adding an electron withdrawing group that's making benzene more stable, it's going to take this energy level right here and make that lower, which actually is going to make the hill even taller because we're starting at a lower energy level. So our deactivating substituents are going to do two bad things. They're going to make benzene more stable in general, which makes it less likely to react, and they're going to make it into a worse nucleophile, which again means that it's going to react much more slowly. So we're going to look at what we can classify into each of these categories. And of course, it's not just two categories. Within each of these, we break it down even further. And so our activating substituents are going to be strong activators, moderate activators, and weak activators. And then the same thing for the deactivating substituents. So there's going to be 6 categories altogether. So we're starting with the strong activators. So remember, all of our activators, anything that falls into an activating category, whether it's strong, moderate, or weak, are electron donators. So as we talk about each of these 6 categories, we're going to look at some examples. That's what's on the bottom of the slide. We're going to give them kind of a generic description. So that's what's right here in the middle. And then for the activators, we're going to talk about how they donate electrons to the ring. And for the withdrawers, the deactivators, we're going to talk about how they withdraw the electrons from the ring. So starting with our strong activators, they contain an electronegative atom with a lone pair without neighboring pi bonds. So it's pretty specific, but it is because we're dividing them into these 6 categories. So the next slide is going to be with that pi bond. And it does make a difference. We'll see why when we look at we'll do a kind of an example practice problem in a couple slides. So if we look at our examples on the bottom there, we have oxygen and nitrogen. They obviously all have lone pairs. Our nitrogen, we have primary, secondary, and tertiary, but they're all nitrogen, so they're all amines. And then for our oxygen, we have an alcohol, and then we have a oxide, so an oxygen with a charged oxygen. Ethers do not fit into this category. We will see ethers pop up in another category, but just our alcohol and our oxide. Now there are other things that fit into these categories. This list on the bottom here, and this goes for all the categories, but the list that's on the bottom are examples. So there are other things. If we think about other electronegative atoms that would have lone pairs, especially ones that are in the same family as oxygen and nitrogen, sulfurs and phosphorus would be a good example to put into this category because they form very similar bonds to oxygen and nitrogen. All right. These are all going to donate electrons towards the ring through resonance. So donating electrons through resonance. And in parentheses after like how they're donating or withdrawing, I tried to make kind of like generic categories or kind of like ways to recognize them, I guess. And they're able to donate electrons through resonance because there's a lone pair next to the ring. So because we have a lone pair adjacent to a pi bond, or if we're thinking back to our chapter where we learned about resonance categories, this is an allylic lone pair that falls into one of our resonance categories. So that's why it's able to. Now, on that last bullet point that I don't have circled yet, it says that it's going to add a negative charge to the ring to make it a better nucleophile. So we will see this in a couple slides. I'm going to draw out all of the resonance for one of these so we can see how that negative charge is in the ring. But really, this is the idea for all of our activators. We're increasing that negative charge to make it a better nucleophile. All right, next on the list then are the moderate activators. So these are still electron donating groups. They just don't donate as well as our strong activators. Again, we have an electronegative atom with a lone pair next to the ring and a neighboring pi bond. So we have esters, we have amides. Here's where our ether sneaks in. So ether doesn't fit that description, but it does fall into this category because of how well it's donating those electrons. So The generic descriptions on there are mine. Those aren't from the book. I was just trying to find a way to categorize them or label them without just having you guys memorize a bunch of structures. So, yeah, there's always exceptions. So again, these guys are all going to donate electrons by resonance because, same reasoning, they have that lone pair next to the ring. So our last group, our strong activators, also have a lone pair next to the ring that they can donate through resonance. These ones, our moderate activators, have a lone pair next to the ring that they can donate through resonance. So why are these ones moderate activators and the other ones strong activators? Why are these ones worse at donating their electrons compared to the other group?
Is it because they can do resonance with the pi bond next to them from the oxygens rather than the pi bond from the benzene?
That is exactly right. So there's competing resonance. The lone pairs on those, on the oxygen and the nitrogen, yes, we can donate the electrons into the ring, and that's going to help the ring out. But those electrons can go towards the pi bond, and that has no effect on these reactions we're looking at or on the benzene ring. So because the electrons are getting pulled in two different directions, it's going to give less electron density to the ring. So let me answer my own question up here in writing. Lone pairs are in resonance with pi bond. So another way to say that is that there is competing resonance. Sorry, I gotta make a little adjustment here. I just felt how hot my tablet was. And I have a desk fan as my cooling fan. So I need to turn it on. My very low-tech cooling fan. It works though. Okay, there we go. All right, so let's look at some actual resonance then. We have our strong activator on the top here, our alcohol attached to our ring, our phenol, and then we have a moderate activator on the bottom. Moderate, our ester. So for our strong activator, we're going, why is the ether less? So the ether, that is a great question, Noah. So let me go back. So the ether falls into the less category because the bond between the oxygen and the carbon is stronger than the bond between the oxygen and the hydrogen. And so because of that, the electrons aren't as free to move as they are when the oxygen's bonded to the hydrogen. So it has to do partly with that dipole moment and, what's the word I'm looking for? The polarizability of the bonds and the electrons that are in them. So it's just not as free of movement. Okay. Our general guideline for drawing resonance with these is if you are doing electron donation, you need to do 2 electron pushing arrows at a time. And if you're doing electron withdrawing, you only need to do 1 arrow at a time. Now, this is not like a hard and fast rule. This is just kind of a general guideline and a pattern that we see. So for our electron donation, I'm going to start at the lone pairs of the oxygen. Now, again, this is going back to, I think it's chapter 6, but the chapter where we learn about all the different resonance patterns. and we have an allylic lone pair. That's what allows us to start this pattern. So I'm going to go from the lone pair, from the lone pair right onto that bond between the carbon and the oxygen. And the reason why we need 2 arrows is if we stopped there, the carbon on the ring would have 5 bonds. So I'm going to do 1 more arrow going from the pi bond onto that carbon. So now I have my benzene ring, and I'm going to draw everything that didn't get affected. And if you have trouble drawing resonance, this is how I would suggest doing it. So what I drew right now is all of the stuff that didn't change. The ring's still there. 2 of those double bonds weren't affected. The hydrogen didn't change. And then here's the new stuff. We now have a double bond between the oxygen and the carbon. And the other pi electrons are now up on this carbon as a lone pair, as a carbanion. Then that carbanion is going to move around the ring in the same pattern, essentially. So we're going to take the carbanion and move it right there. It's going to create a new double bond. And we're going to take the other pi bond and put it right there as a lone pair on the neighboring carbon. Again, I'm going to draw all, I didn't put my first oxygen over here needs a positive charge. So I'm going to add that in. I'm going to draw all of the stuff that doesn't change. So we still have that double bond on our oxygen. This double bond had no changes to it. So then when we look at what changed, we have a new double bond right here. And then that last carbon ends up with the lone pair and the negative charge. And if you're doing this and practicing it and you reach a point where you're annoyed because it feels like you're doing the same thing over and over again, that's a good sign, because it means you understand that it's just repeating and it really is just the same thing over and over again. So we're going to take the lone pair, we're creating a pi bond, we're going to take the pi bond, and we're going to make a lone pair. So on the test, if I'm asking you for resonance, you do have to draw all of these. So again, there's the part that didn't change. My new pi bond is now right here on the bottom, and my new lone pair is right over here. And then 1 more. I'm going to take that lone pair and go right here. And then I'm going to take the pi bond between the carbon and the oxygen, and it's going to make another lone pair up on that oxygen. And I'm going to draw my last structure up here just to put it out of the way for our second one. So again, that's the part that didn't change. I have a new pi bond right here, and then I have my 2 lone pairs on my oxygen. So altogether, this structure does have 5 resonance contributors. The very first one and the very last one look super similar. The only thing that's different about them is the location of the pi bonds within the benzene. But remember, that's what makes benzene special, is it has the resonance within that structure. So it does count as its own unique resonance contributor. The other thing I want to point out about this structure is notice where that negative charge lands in relation to the substituent that's already on the ring. So if we look at where that alcohol group is and where that negative charge is, it's on the ortho carbon, the para, and then the other ortho. So when we add a second substituent and we have an electron donating group on the ring, we've activated the ortho and the para positions. We've made those specific carbons into really good nucleophiles because that's where that carbanion, that lone pair, rotates to as we go around the ring. So last Wednesday, I kept pointing out how that charge goes to every other carbon. It definitely plays a role in how we are either activating or deactivating certain positions. Any questions about that first one? Okay, so let's look at the second one. We're not going to go through all of them, but we do want to talk about how it is different. And we're going to show the different one first. So our oxygen is next to a pi bond. That's what makes this one unique, or that's what puts it into this category. So my first resonance structure is actually going to be to put the pi bond between the oxygen and the carbonyl carbon. So the benzene ring is not affected at all, but this is still an important resonance structure to know because it is showing us why it's not as good at donating electrons to the ring. It has to share them with that carbonyl. So we end up with that as a resonance structure. So I'm going to put those electrons right back where they belong, get back to where we started. So what I'm drawing right now does not count as a different resonance contributor because it is exactly the same as the first one. Let me make it exactly the same. My pi bonds are not in the exact same spot. There we go. All right. The rest of this is actually going to look exactly like the one above. We're just going to go from that oxygen onto that carbon. I'm just going to draw this next one here. So again, everything that's on there right now is the stuff that was not affected by those resonance arrows. And so we created a double bond between the oxygen and the carbon. So now our oxygen is positively charged, and that pi bond became a lone pair on our carbon. Another thing to kind of check yourself as you're drawing resonance is your overall charge should stay the same. So with our starting structure, it is neutral. So all of our other structures need to be neutral overall. So that means if you have one positive charge, you should also have one negative charge. So just kind of something to keep in mind as you are drawing your resonance contributors. The rest of this will look exactly like the one above it. So that also means that the ortho and para positions are going to have that negative charge. They're the ones that are going to be activated. But it does have some pull going towards that pi bond, which just makes it a little bit less of an activator or an electron donator. Questions about either one of these so far? Okay. So that takes us to our last activating category. And our last activating category are the weak activators.
Sorry, Professor. I have one question about the model.
Yeah.
How many resonance contributors were there in total?
Whoops, wrong way. So there would be 6. So we would have, if we start that at 1, I'm going to ignore that next one for a second, and 2, we would have essentially the same 5 that the one above it has, plus this extra one would be our sixth one.
Okay, thank
Does
you.
that make sense?
Yeah.
Okay. So our weak activators are carbon groups. We do have a lot of examples of different carbon groups down there, but it's to emphasize that it can be methyl, primary, secondary, tertiary. They're all going to do the same thing. These are activators, so they are electron donators, and the way that they're donating electrons is by hyperconjugation. And so we will have hyperconjugation anytime there's a carbon bonded to the ring. So let's talk about hyperconjugation. We first talked about this term when we learned what a carbocation is. So when we have a carbocation, it is sp2 hybridized, which means that it has this empty p orbital. Empty p orbital. The reason why a carbocation with more substituents is more stable is when we have another carbon bonded to it, that carbon has bonds, whether they're to hydrogens or other things. So these electrons right here in the sp3 hybridized orbitals of that neighboring carbon can overlap into the empty p orbital of our carbocation. That overlap right there is hyperconjugation. So the overlap of the sp3 orbitals into the empty p orbitals of a carbocation. All right, the reason why we're talking about this here is, I'm going to go back a few slides. Going back to the reactions we talked about last week, the second part is all of that resonance stabilization. In the middle of this mechanism, there's a carbocation transition state. So the way that our alkyl group can help is by helping to stabilize that carbocation. And it's donating its electrons, but it's not through, because it's not through resonance, we can't draw arrows to show it. So there's essentially two ways that electrons can move in a structure. One of them is resonance. We can draw very definitive arrows. They start here, they end here, they're getting shared between these two locations. The other way that electrons are moving is within the electron cloud, which is kind of thinking of it more as like MO theory, or we have to think of all the electrons in a molecule as belonging to the entire molecule. And so that electron cloud can kind of shift or squish towards things it's attracted to or away from things it's repelled by. And that's what hyperconjugation is. We can't really show a resonance arrow showing the movement of those electrons, but we can say that the electrons are moving into that orbital to help stabilize it. So I bring that kind of weird discussion up because it is going to come up. That type of movement is going to come up in another category. So long story short with this guy is that because there's a carbocation transition state, having a substituent that can help stabilize that carbocation is going to make our transition state more stable. It's going to put it at a lower energy level, which is good. There we go. So the donating electrons by hyperconjugation, this is going to help stabilize our carbocation transition state. Questions at all about our weak activators? Okay, then we are switching over to the deactivators, starting with the weak deactivators. And remember, all of our deactivators, what they have in common is that they are all electron withdrawing groups. So we're essentially going through the same stuff. We're going to look at what substituents fit into each category, how they're withdrawing electrons, and then how that's affecting the molecule or the reaction. So our weak deactivators are the halogens. So nice category. It's very cut and clear and makes sense. Now notice on that list, it tells us that they are donating electrons and withdrawing electrons. So that means there's actually, again, two competing actions taking place here, which is why they're weak deactivators. So they are withdrawing the electrons, but there's a competing force to donate electrons. So they're not very good at deactivating the ring. Let's talk about how they donate first. They can donate electrons by resonance because they have a lone pair next to the ring. So same thing we saw with oxygen. We can go from that lone pair. We can do that going all the way around the ring. Now this is not a very strong donation from a halogen because that's going to give a halogen a pi bond. It's going to give a halogen a positive charge. So the halogen itself is not going to be very happy. They can also withdraw electrons through induction. So this is not an electron movement arrow thing. It's a dipole moment. I said it's not an arrow thing, and I'm going to draw an arrow. It's not an electron pushing arrow. So if we look at, actually, I'm going to draw a little bigger so I can put my dipole moment in here a little bit easier. There's my bromine. Our halogens in general are more electronegative than our carbons. So because it's more electronegative, within that bond between the carbon and the halogen, our halogen is partially negative, our carbon is partially positive. So we can show a dipole moment going towards that halogen. So this is that electron cloud thing again. The electrons are going towards our electronegative atom, towards that halogen, because it has that electronegative pole. Electronegativity is its attraction towards electrons, or its ability to attract electrons. And so because of that, it is pulling the electrons away from the away from the ring, or withdrawing them from the ring. And then the last thing on there, it says that this is the more important force. So the withdrawing overpowers the donating is essentially what that's saying. So halogens are classified as deactivators because their withdrawing abilities are stronger than their donating abilities. Questions about the halogens? Okay, then let's look at moderate deactivators. So our moderate deactivators are carbonyls. And so essentially we've seen these before, but flipped the other direction. And what I mean by that is we've seen esters before, but that single bonded oxygen was on the benzene side, and this time it's on the opposite side. So the difference is that with our moderate activators, we had a electronegative atom with a lone pair right next to the ring. And now we have a carbon right next to the ring with a pi bond and those electronegative atoms. So have to pay attention to what's directly bonded to the ring. So we do have an ester, we have ketones and aldehydes, carboxylic acids, amides. This is our sulfone group that we learned how to add on last week. And then we have our cyano group. So technically those last two don't contain carbonyl groups, but they do have a pi bond adjacent to the ring. So the carbonyls are the larger group, but the other two fit there because of that pi bond. So again, they do withdraw electrons, and they can withdraw electrons two different ways. They can do it by induction. So again, this is the dipole moment thing. We have electronegative atoms, so we could draw a dipole moment going towards the oxygens, nitrogen, sulfurs, whatever it happens to be, but we could draw that dipole moment going from the ring towards that substituent. So the electrons are being withdrawn through the induction force because we have that difference in electronegativity. And then the stronger force is that they can also withdraw electrons through resonance. And our thing to look out here is that we have an sp2 carbon adjacent to the ring. So we have a carbon that can participate in this resonance. I do have one to practice. Oh, I think it is on the next slide. Okay. And then our last bullet point here, which we will see on the next slide, but remember these are our deactivators, so they're making the benzene less reactive. It's going to add a positive charge to the ring. If it's withdrawing electrons from the ring, it's making it more positive, and that's not going to be good if we're trying to react it as a nucleophile. So we're going to look at the resonance for this ester group. And I'm going to start right here. Now, electron donating that we saw a few slides back, we needed to do 2 arrows at a time because we needed to move. I kind of always think of it as you have to move the electrons and you're moving the charge. It's not totally accurate, but I guess in my mind, that's kind of how I reason it out. With electron withdrawing, because the charge is positive, we don't have to show arrows to show the movement of that because it's a lack of something. It's not that there's something extra. I'm starting with this arrow. Going back to chapter 6, when we talk about resonance types, one of the resonance patterns is a pi bond between atoms of different electronegativity. So that can be the start of the rest of the chain of events because we have an oxygen-carbon pi bond. So here's what we end up with. The benzene ring is going to look exactly the same because nothing has happened to it yet. So the only thing that's different is that carbon-oxygen pi bond is now a lone pair on that oxygen, and we have a carbocation next to the ring. So now there's 2 different things that can happen at this time. If I'm going to draw my arrow going towards that carbocation, where can I start my arrow? Yeah, we can definitely start from the pi bond in the ring. So I'm going to go from right here to right here. So I'm going from the pi bond to the new pi bond's location, so to that sigma bond. So there's all the stuff that wasn't affected. There's all the stuff that didn't change. My new pi bond goes right here, and there's my new carbocation. where else could I have started my arrow? So to stabilize that very first carbocation, where else could I have started my resonance arrow? Yeah, the other oxygen, exactly. So I can go on, I'm just going to draw it in a different color, but we're going to go right here. So this doesn't actually affect the benzene ring, but it is going to end up being important. So that is, again, another one of our resonance contributors. It does help stabilize that carbocation, even though it's not directly affecting the benzene ring. So if we're going back to that carbocation that is now on the ring, now we can keep doing our little pattern going around the ring. And we are only doing one arrow at a time. So I generally have seen that students find these ones a little bit easier because it is just the one arrow at a time. And we're more used to carbon having a positive charge. So we're used to dealing with carbocations more often than carbanions. So I'm just going to go right here. And again, that fits into our pattern because it is an allylic carbocation. And that was one of our patterns that we saw back in, I keep saying chapter 6. I'm not 100% sure if it was chapter 6. Back in our resonance pattern chapter. So there's all the parts that weren't affected, that didn't go through any changes. My new pi bond is right here, which means that that carbon on the bottom is now my carbocation. One more time. A weird pattern to my resonance here, kind of going zigzagging around my slide. Just want to make sure I didn't run out of space. It's weird to try and learn how to draw all of this, whoops, on a slide instead of a giant whiteboard. Okay, so there's all the stuff that was not affected. My pi bond moved to over here. It's not the prettiest benzene ring, but it'll get us through, which means my carbocation is right there. And we're not done. This has a lot of resonance. So now we're going to go back to the pi bond that's outside of the ring. We're going to go right there. Don't be tempted to draw more than one arrow at a time. If the test question is asking you to draw all of the resonance contributors, and I also drew this arrow at the same time, that would actually cause me to miss one of my resonance contributors. It would cause me to skip over one. So just be careful how many arrows you're drawing at once. So try and use the one arrow at a time for withdrawing, 2 arrows at a time for donating. Let's see, OR, oxygen negative. So again, that's the part that hasn't changed. My pi bond is now down there, and my carbocation is up there, and we have one more. Okay, we are back to the beginning. So again, the very first one and the very last one look super similar, but those pi bonds in the benzene ring have shifted. So what do we end up with? 2, 4, 6, 8 resonance contributors overall. Yeah, a benzene ring stamp would be excellent. They do make graph paper that has hexanes on it instead of squares. So if you really want some assistance. A ton of resonance contributors. So remember our deactivators, specifically in this category, are deactivating the ring through 2 different ways. The first one is they actually stabilize the ring on its own. So ignoring any reaction we're trying to put the benzene through, a benzene with this electron withdrawing group on it is just a stable structure because it has 8 resonance contributors. So if something is more stable to start with, that means it's going to be even harder to react. So the fact that we can draw these 8 resonance contributors makes it a slower reaction.
Wait, Professor.
Yes.
Once you have the reformed benzene, can't you also go through that same process that puts the double bond on the oxygen bonded to the other carbon group?
That's true. So we would have a 9th one. So essentially this one, but with the benzene bonds in the opposite positions. Is that what you mean?
Exactly.
Yeah, so there would be a 9th one, you're right. So the second reason why this gets labeled as a deactivator is that positive charge that is rotating around the ring. We want benzene to be a nucleophile for all of these reactions, and if there's a positive charge on the ring, that means it's not going to be a good nucleophile. Nucleophiles need to be electron rich. Notice where this positive charge is at. Ortho, para, and then ortho again. So we have deactivated the ortho and the para positions for this nucleophilic reaction. So eventually, where we'll get in just a couple slides, is we're going to look at the sterics of it. Is our substituent going to force the second substituent into an ortho, para, or meta position? And because these deactivators have deactivated the ortho and the para positions, that leaves the meta positions available for addition or for the substitution reactions. So there's our 2 reasons. It's just a more stable structure, means it's harder to react, and we've added a positive charge onto the ring, specifically in the ortho and para positions. All right, one more category. Last one are the strong deactivators. So in our strong deactivator category, notice I don't have like my little summary bullet point down here because there's not really a way to summarize these. We have our nitro group. And just a reminder, when our nitro group is bonded, it looks like this. And we have a nitrogen with a positive charge. So this is an ammonium. And then we have a carbon with 3 halogens attached to it. So a trihalide carbon. So again, they're all deactivators, which means they're all withdrawing electrons. All of them can withdraw electrons through induction. Our trihalide definitely has the benefit of electronegativity. We have those 3 electronegative atoms bonded to our carbon. So it's going to pull the electrons from the ring through induction because of that dipole moment. And with the NO2, same thing. It's going to pull those electrons towards that NO2 group. We have 3 electronegative atoms there, the 2 oxygens and the nitrogen. The ammonium's a little bit different. It's not an electronegativity or a dipole thing. The nitrogen has a positive charge, and so the electrons are just going to be attracted to that positive charge because opposite charges attract. So it is pulling the electrons towards it because of the opposing charges. And then our NO2 group also has resonance. So just the NO2, but it can pull those electrons through with resonance. So let me draw just our little NO2 group up here again. So if we are withdrawing electrons, we can do, and I know I just did 2 arrows at a time, but it's to show you one of our resonance contributors. So a little bit different of an approach because it's nitrogens and oxygens, but same result as what we saw in the last slide. We end up with that positive charge on the ring, ortho to the substituent that's already there. And so it's going to go around the ring in that ortho, para, ortho pattern, deactivating those positions because we've withdrawn the electrons from the ring, or another way to think about it is we've made the ring more positively charged. All right, we have 6 categories. Here's a table. So this table is from your book. It essentially sums up all of the categories. We have the activators on the top half, strong, moderate, and weak. We have the deactivators on the bottom half, weak, moderate, and strong. So they're in order. The very top of the table are the ones that are going to make the reaction go the fastest. And then the very bottom of the table are going to make the reaction go the slowest. So where we are headed with this next is the right-hand side of this chart. Ortho-para director and a meta director. And notice where that divider line is right here. So our categories, what we're looking at is we're looking at if one of these substituents is already on the ring and we want to add a second, where will the second add? The activators and the weak deactivators, or another way to say that would just be to say the halogens. So the activators and the halogens will push the second substituent to add at the ortho and para positions. The moderate and strong deactivators will push the new substituent to add at the meta position. And so we've talked a little bit about why this has happened, but that's where we're headed with this now, is to talk a little bit more about the why. Our ortho, and I kind of said all this, but the ortho para directors, activators, and halogens, all of these groups are able to donate electrons through resonance or hyperconjugation. So even though our halogens are deactivators, they can donate electrons to the ring through resonance. Our meta directors are all of our moderate and strong deactivators, and really the one thing that they all have in common is they can't donate electrons. We can't say that everything that withdraws electrons falls into this category because the halogens are kind of the weird gray area. So really we're deciding, can they donate electrons or can't they donate electrons? And that's where we're making that divider line. The example on the bottom is showing us what we end up with. Our starting material there, toluene, so benzene with a methyl group. We're adding bromine to it. And because our methyl group is one of our activators, our bromine is going to add to the ortho and the para position. Now, you might be questioning, or your thinking might be headed towards, well, which one of those is major and which one of those is minor? We'll get there in a couple slides. So this is a ortho para director. With our NO2 group here, this is a meta director. So our product is going to have the bromine at the meta position. I'm going to take a step back just for a second. So for the exam, when you are given a substituent, a methyl group, an NO2 group, you should be able to tell me if it's a activator or a deactivator, if it's a strong, moderate, or weak activator or deactivator, if it's donating electrons or withdrawing electrons, and how that's happening. So resonance, hyperconjugation, induction, and essentially understand why that would be activating or deactivating. You're not going to have an essay question on the test, but understanding it's definitely going to help you solve problems. If you're given a substituent, you should also be able to say whether it's an ortho-para director or a meta director. Now, you're not going to be able, or you're not going to have to answer all those questions for every reaction, though. For example, if you were just given this and said, what is the product? All we need to know about that methyl group is whether it's an ortho-para director or a meta director. We don't need to know what the bromine is because it only matters what's already on the ring. We also don't need to know if the methyl is a moderate or a weak activator because both of those fall into the ortho-para directing category. So I bring this up because when you are taking the test or doing the worksheets, it can be easy to overanalyze things or go too far. I know sometimes with questions that you're unfamiliar with, you might not know where to stop or figuring out information. This is something that I see with resonance even. You just want to keep drawing more and more structures and arrows. So if you're filling in products, all you need to know about your substituent is what type of director it is. All right, so where we're going in our next couple slides then is why are they ortho-para directors and why are they meta directors? So we're gonna start by looking at our weak activators, so our carbon groups. So these are electron donating through induction, and the only thing that really falls into that category are the weak activators, which are our carbon groups. So this is looking at the very first step of that mechanism. So all of these start with our benzene ring with a methyl group attached, and we're reacting all of them with a nitronium ion. So this is the result of nitric acid and sulfuric acid creating a better electrophile. So this goes back to the reactions we talked about last week. All three of these are showing the same thing, but at different locations. So in the first one, we're adding that nitro group ortho to the methyl. The next one's meta, and then para. So the first one for all of them, all of these, what we're looking at is that nucleophilic attack. So we're going from the pi bond of the benzene ring towards our electrophile. What's in the boxes in the middle is that resonance stabilization of that transition state. So again, it's the same thing for all of them. We have a carbocation that's moving around the ring as the pi bonds move around the ring. So they each have 3 resonance contributors. Really, there's not a whole lot different about any of them. There are 2, though, that are highlighted in green. Why are these 2 singled out? What makes them different than all of the others?
They have a tertiary carbocation, right?
Exactly. So in both of those resonance contributors, both of the ones that are in green boxes, the carbocation is at the location of that methyl substituent. So I've pointed this out many times now, but as that carbocation moves around the ring, it hits every other carbon. So if we add our substituent ortho or para to our methyl group that's already on the ring, as that carbocation moves around the ring, it hits that carbon where it hits the benzene carbon where our substituent carbon is attached, giving us a tertiary carbocation. And we know, of course, that tertiary is more stable than secondary and primary. So what this tells us is that when we add a substituent, ortho or para, it's going to make our resonance contributor more stable because it's going to be tertiary instead of secondary. So those two resonance contributors are the most stable out of all of the options on there. So our weak activators are ortho-para directors because they help stabilize the carbocation when our substituent is added to those specific locations. So I mentioned the major minor thing. So here's our percentages for a methyl group. The ortho product is 63% of our product. The meta is only 3%. So looking back, I'm going to go back one slide. The meta is not a bad option. It's just that the ortho and the para is better. So with that being said, the meta is only 3%. So really, we just ignore the meta. We pretend it doesn't really happen. It's not enough to make a difference. The para is only 34%. So in this case, obviously the ortho is the major. And it's really a statistics thing for this one. There are 2 ortho positions and only 1 para position. So the ortho is approximately twice as much as the para. This isn't true for all of them though, and I'm going to skip a couple slides. I'm going to go right here. So this is showing the same reaction that we looked at on the top here, our benzene with a methyl reacting it to add an NO2 group. The next one is the same reaction, but now instead of a methyl, we have an ethyl. And then the bottom reaction, we have an isopropyl. And look at our percentages. So let's see, ortho, para. With the methyl group, the ortho is the major product. With the ethyl group, it's 50-50. And then with the isopropyl, the para is the major product. This is steric hindrance. So we like to use that term steric hindrance to explain lots of things. And really it's just a way to say there's too much stuff in the way. So as soon as we get anything larger than a methyl group, it's going to be easier to bond to the para position because there's just less bulkiness in the way. So if we have a methyl substituent, our major product will be the ortho, and anything larger than a methyl, our major product will be the para position. Ethyl's kind of in that weird in-between zone, which means it won't be on the test because that's just annoying. I wouldn't ask you that. But this is our divider. Methyl is ortho, everybody else is para. So really, if we get anything of any size. All right, I'm gonna go back. Oh, too far, right here. Our moderate and strong activators are donating electrons also through resonance. And so we saw this. I drew out these resonance contributors, and we saw that we get a negative charge, a carbanion, at the ortho and the para positions. So it's going to make those specific carbons really good nucleophiles, and our second substituent is going to easily add to those positions because they've been activated. The reaction that's on the bottom there is showing us that adding a bromine to this ring is so easy that there's no catalyst needed. And we end up with polysubstitution, so adding the same substituent more than once. It can be a little bit hard to control just because we've activated so many carbons on that ring. I'm looking at my notes here, see if we need to think. That was it, yeah. Oh, yeah, go ahead, Nate.
So for a anillium ion, you know, where the NH3 with the positive charge on it, so that's more inductively deactivating than a halogen, right?
Yes, if our nitrogen has a positive charge, yeah.
And is it because of that positive charge?
It is. So it's going to pull those electrons away from the ring, whereas a halogen can also donate towards the ring because it has a lone pair. But if our nitrogen has a positive charge on it, it's not going to have any lone pairs on it that it can do donation with.
Thank you.
You're welcome. So we talked about the resonance before anything has added. So this is our benzene ring with one of those moderate or strong activators on it, and it's showing us that it's activating those specific positions. Same reaction, but now we've added that substituent onto the ring in the ortho, meta, and para positions. And again, we get a carbocation that's moving around the ring. We have two resonance contributors that are highlighted in green here. And the reason why those ones are highlighted in green is because they exist, which sounds kind of weird, but because we have a positive charge that's moving around the ring, it can land right where that substituent is at. So right there in our first structure, or right here in that middle structure, and the oxygen lone pair can go towards that carbocation, and it adds a fourth resonance contributor. So these aren't highlighted because they're more stable than the rest. They're highlighted because they are a fourth resonance contributor. And when we're in the meta position, that carbocation skips over our oxygen substituent, and it's not able to add that fourth contributor. And we know that the more resonance contributors we have, the more stable it is. So just the fact that that fourth one is there makes it extra stable. And then same reasoning with major and minor. A methoxy group is larger than just a methyl. So our major product is the para. And again, we are ignoring that meta. It's not a big enough percentage to make a difference. Oh, we talked about that slide, obviously. So on to our deactivators. We've looked at this resonance, not specifically for nitro, but we've looked at it for our electron withdrawing groups through resonance. So this happens with our moderate and strong deactivators. There is a carbocation moving around the ring on the ortho and the para positions. So it is deactivating those locations. So as a result, our second substituent will add meta. Not because the meta has been made more reactive, it's just because it has not been made worse, which the ortho and the para have. So, and actually I'm gonna go back one more slide just to add to this. We're looking at a lot of resonance, obviously, today. This is our resonance of just the structure with that initial substituent. So before anything has even reacted. Now we're looking at what if we add that second substituent, what do the resonance contributors of that transition state look like. So we have our electron withdrawing group on the ring. We're adding in a second substituent in the ortho, meta, and para positions. Again, we have two that are highlighted in green, this time for bad reasons. So these two are highlighted in green because they are the least stable of all of the resonance contributors on the screen. Because we have that positive charge right next to that electron withdrawing group, that's going to make it even less stable. So because of that, the meta option is going to be the best for our strong and moderate deactivators. All right, last slide here. We're going to fill in some products. So we have a benzene ring with an isopropyl group, and we're adding fuming H2SO4 to it. So what type of director is our isopropyl group? Is it an ortho-para director or a meta director?
Para?
It is para, so technically ortho-para. They come as a group. Para will be our major though, because it is kind of a big structure. So we're going to draw both. So I'm just going to start by drawing what we started with. And fuming H2SO4, this is what we're going to use to add on an HSO3 or a sulfone group. So I can add it para, or I can add it ortho. And our para will be the major product because of the steric hindrance. And then what about that last one there? We have an NO2 group. Is our NO2 a ortho-para or meta director?
Meta.
Good. So again, I'm going to draw just my starting structure. And we are adding chlorine with aluminum chloride. So that's just going to add a chlorine to the ring. The aluminum chloride is our Lewis acid catalyst. And there's my meta position. So this one only has one product. We don't need to draw both metas or both orthos because they're identical to each other. Questions about either of those products, about either of those reactions? Okay, so where we're headed with this on Wednesday then is, now that we have two things on the ring, where will the third thing add? And it's going to kind of lead us into multi-step syntheses. So if we have a benzene ring with 4 substituents on it, what order will we add them on? How do we create that final product? Okay, so that is it for lecture. We will chat about lab though, so go click on the other Zoom link and we will go over the lab for today. So I will see you in a couple minutes.
Thank you, Professor.
Thank you.
Professor, I have a question.
Yeah.
Can you kind of help show me like visually like how to pick the difference, or like how to tell like something's electron donating or electron withdrawing?
So the biggest thing, I'm going to go back up a few slides here. There we go. I was trying to move my little video. For electron withdrawing groups, there is going to be a pi bond next to the ring. Now, this is not the case for all of them, but it's kind of a good spot to start. So all of these have a pi bond next to the ring, so they can pull the electrons away from the ring towards that pi bond. And then our electron donating groups have a lone pair next to the ring. Now, one of the things that we didn't quite get into because well, A lot of our substituents can do both. We didn't talk about all of the different ways that they can do both, but that can be one of the things as you're trying to reason it out, that it can be a little bit confusing if you're trying to think it out in your head. So stick to those two guidelines to start with, and then for each of these, on the slide here, when I put down, that it's donating through resonance or donating through induction, I tried to put in parentheses why it fits into that category or why it can do it that way. And so use that as your reasoning. Does that make sense?
So when it says donating electrons, that means does that mean that it's electron donating then?
Yeah.
Okay.
Yeah. So if we look at our table here, when we're looking at patterns, we have lone pairs next to the ring.
Right.
And when we have our electron withdrawers, we have these pi bonds next to the ring. So that's the biggest pattern for them. So electron donating, lone pairs, electron withdrawing, pi bonds.
Okay, thank you.
It's a good start.
Okay, I'll see you in lab